In this video I'm going to show you another integration technique, and it's called parts. And like substitution, it works for carefully engineered integrands, and I'm going to show you how to use that right now. So here's an example of two separate, similar but different integration problems. So what if I asked you to evaluate the antiderivative of x times sine of x squared dx? Okay, and then a little difference would be the antiderivative indefinite integral of x times sine of x dx. Now they're very similar, and what we're establishing is that this guy right here is a nice integration by substitution problem, because if that's my u, then everything else that's left will be maybe not exactly, but certainly a multiple of du. And so by a simple substitution, the 1/2 du ends up being x dx, and that ends up being sine of u, which I can then integrate. The 1/2 comes down as a coefficient, and sine of u, the antiderivative, is negative cosine of u, and I'll just plug that u back in and throw in my constant of integration. Okay. Now what happened in that particular problem is that the sine of u, if u were x squared, the x dx gets swallowed up by 1/2 du. So we're able to rewrite this integration problem in terms of a u and a du, and then integrate appropriately. That's not going to happen on this one on the right. Okay, and it's not going to happen because, well, it's just not. If u is sine x, then du would be cosine x dx, and then what are we going to do with that x out here? So, well, so u, let's pretend that's going to work. Oops, sorry, wrong way. So let that be u. Du would be cosine x dx, and that's not going to get rid of that x right there. So I guess we can solve for x here from our sine of x, but that will give us an inverse sine function, which is even messier than what we have here. Okay, so all that said, parts is going to be required. Substitution is not helpful. Substitution just doesn't work. Not helpful. Okay, so rest assured there is a technique, and it's called parts. So I'll give you the general form for it right here. In integration by parts says this, and it's very general, and I just ask you to believe this without verification. We'll talk about why it works at a later time. But if I can get the antiderivative of u dv, then by this rule, by the parts rule, it's going to be equal to the product of u times v minus the antiderivative of v du. Now here's where that's helpful. When I integrate a u, I ended up here with a du within the integral. Okay, and you'll see how that becomes helpful right now. So let's go back to this example here that I threw up here, the antiderivative of x sine of x dx. And what I need to do is I need to make this integrand fit the model of u dv. So I'm going to let u be x, because when u is x, I end up with a du trapped within my integral. Okay, and that's doable. So what's going to happen is this. My u is going to be x. Actually, I'm going to put it out here to the side. And if u is x, then du, the differential u, is 1 times the differential x. Right? And so what this rule says, if that's my x, then everything else has to be dv. It has to fit this model, this structure, u times dv. So dv is going to be sine x dx. Okay, and if I know what dv is, the differential, then v will essentially be the antiderivative. So the antiderivative of sine is going to be, the antiderivative of sine is going to be negative cosine. Okay, so again, recall, to go from u to du you differentiate, to go from dv to v you integrate. Derivative, antiderivative. Okay, so now I have my little chart over here, so I'm just going to plug it back in. So that's equal to u times v. My u is x, my v is negative cosine x, right? My u, x, times my v, negative cosine x, minus the indefinite integral of v, and my v is negative cosine x, times du. And du is just dx. Okay, great. Now I'm going to take this negative sign, I'm just going to pull it out. Plus cosine x dx. And now if you see what I have here is I now have a form, an integral, which I can integrate. Right? That's easily integrable, right, for lack of a better expression. So now I know that the antiderivative of cosine is going to be sine of x. So I integrate the cosine of x dx becomes sine. And I'm just going to make this look a little bit better out here. And throw in my constant of integration. Okay? And so look what happened with my u, my x, here's my x here, to my du, dx. So what essentially I did is I knocked the power down from an x within the integral to a dx within my second integral, which is part of the integration by parts. Okay, and let's again verify and see if that is indeed correct. So here's my check. I'm going to take the proposed antiderivative and I'm going to differentiate that guy. So negative x cosine x plus sine of x plus c. Got to use a product rule here, right? The product rule says take the derivative of the first piece, which is negative x, which is negative 1, times the second, plus the first piece times the derivative of the second. So the derivative of cosine is negative sine x, plus then the derivative of sine, which is cosine of x. And then I got to clean that up. I got negative cosine x minus, plus x sine of x plus cosine x. See you later. X sine x and x sine x. That's what I want. Okay. So this method is called integration by parts. Here is a general rule which we have to make fit. Okay, and in general we want u to be the polynomial term for now, because if u is x, then my du becomes dx. So I've bumped the power down from an x just to a dx. Now, something to consider, if that were x squared out front here, or even x cubed, we can do this model, but we might have to do it 2 or 3 times. That's something we'll think about in class tomorrow. So this is integration by parts. It's another technique for the creative art of integration.